Confusion matrix, as the name suggests, it gives us a matrix as output and describes the complete performance of the model. So let's assume that we have a binary classification problem. We have some samples belonging to two classes, yes or no. Also, we have our own classifier which predicts a class for a given input sample. So if we perform a test on some samples, then we get the following result. This is a very important table, by the way, and you can always refer to it. There are four important terms when we're talking about the confusion matrix: the true positives, true negatives, false positives, and the false negatives. The true positives are the cases in which we predicted yes and the actual output was also yes, which is true, yes or true. The cases in which we predicted no or false and the actual output was also no or false, that is the true negatives. The false positives are the cases in which we predicted yes and the output was no, and the false negative are those cases in which we predicted no and the actual output was yes. So accuracy for this matrix can be calculated by taking the average of the values lying across the main diagonal, that is the true positives plus false negatives upon the total number of samples. And confusion matrix, it forms the basis for other types of metrics. Let's talk about the area under the curve, AUC, which is one of the most widely used metrics for evaluation. It's used for binary classification problem. The AUC of a classifier is equal to the probability that the classifier will rank a randomly chosen positive example higher than a randomly chosen negative example. And before defining AUC, let's understand two basic terms. These are sensitivity and specificity. Sensitivity or true positive rate is defined as the true positive upon false negative plus true positive. It corresponds to the proportion of the positive data points that are correctly considered as positive with respect to all positive data points. The specificity or false positive rate is defined as the false positive upon false positive plus true negative. The false positive rate corresponds to the proportion of negative data points that are mistakenly considered as positive with respect to all negative data points. So FPR and TPR both have values in the range from 0 to 1. They are both computed at threshold values and a graph is drawn. So the area under the curve of the false positive rate versus a true positive rate is given by any kind of this the receiver operating characteristics curve, and it has a range from 0 to 1. So the greater the value, the better is the performance of our model. Another concept is the F1 score, which is used to measure a test's accuracy. So the F1 score is the harmonic mean between the precision and recall. We'll explain the precision and the recall terms. So the range for F1 score is again 0 to 1, and it tells you how precise your classifier is as well as how robust it is. That is, how many instances it classifies correctly and how many times it does not miss a significant number of instances. So high precision but lower recall, it gives you an extremely accurate value, but then it misses a large number of instances that are difficult to classify. And the greater the F1 score, the better is the performance of a model. And mathematically is represented as by this formula, which is the harmonic mean. So it tries to balance between the precision and the recall. Now let's understand these terms. Precision is the number of correct positive results divided by the number of positive results predicted by the classifier. Recall is the number of correct positive results divided by the number of all relevant samples, that is all samples that should have been identified as positives.